Now we will see why do we use three-phase system in place of three single-phase systems. The three-phase system has its own advantages as compared to the single-phase system. The most prominent one is that we have reduced capital cost and operating cost. And the second advantage which we have in using three-phase system is that the total three-phase power is independent of time. It does not vary with time, and due to that, the mechanical input is not pulsating. That is, it does not change with time, and there are no mechanical vibrations in the shaft, and the stability of the machine improves. So the life of the machine also improves. These two advantages help us to determine that we should use three-phase system wherever it is possible, at least for the large machines, so that the mechanical vibrations are reduced. And the one is due to financial benefits. That's why we use three-phase system as in place of three single-phase systems. I will prove all these comments first one by one. First, it has reduced capital cost. Capital cost and operating cost also. The capital cost means the cost during investment, that is while we are putting the system in place, while we are installing it, it involves a major chunk of money, and that is known as capital cost. The capital cost of three single phase systems will be higher as compared to this three phase system, and also the operating cost of three phase system is a little bit lower as compared to three single phase systems. How? We will see. Let us see. If I use three single phase systems in supplying three phase load or three different loads, how I will do that? Let us say there is one source. It will supply one load. This will use one wire for carrying the current, the other wire, second wire, for returning current. Similarly, the second source will give second load. Let us say it is load 1 and load 2. It will give load 2 power through wire number 3, and the current will return through wire number 4. Similarly, the third source will deliver power to the load 3 via wire 5. The current will return via wire 6. So we see in delivering power to three different loads, we require 1, 2, 3, 4, 5, 6 number of different wires, and also the current going here will be same due to Kirchhoff's current law. Similarly, the current going here, let us say of different magnitude, but the returning current will also be same. Similarly, here also the going current and the returning current will be same. This will require that we use the cross section of wires, the going wire and the return wire, to be same. That is, both wires should have same ampacity, that is current carrying capacity. Because of this, the cost of wire will be doubled for every single phase. Now let us say I deliver these three loads using three phase system. I will connect these three loads in a three phase. Let us say this part A, part B, part C, and let's say load 1, load 2, load 3, and I will connect it to a three-phase supply. Let us say it is source 1, source 2, and source 3. Even if I don't connect these two neutral points, then there will be no neutral current. Due to KCL, the sum of these three line currents will have to be 0 because there is no other path for the current to flow. So you see, I am delivering the same power to those three loads using only wire number 1, number 2 and number 3. So only 3 wires will be required with the same 3 source and 3 loads for delivering the same power as compared to the 6 wires which we would have required if we had delivered the load using 3 different single phases. And one more thing, let us say I connect this neutral wire. Okay. As we know, this neutral current will be sum of these 3 phase currents, and if these currents are balanced, it will be 0, and if it is not balanced, then it will have some magnitude and some angle. As we know, this magnitude is going to be lower than the sum of these 3, since this will have some phase differences. So this magnitude will be lesser or equal to the sum of these 3, since these 3 currents are at different angles. Because of that, the cross section or the ampacity of this wire, this neutral wire, will be lesser than these 3 line wires, and the cost involved in this will be reduced. So we see that the capital cost in putting a 3-phase system is quite lower. Rather, I would say it is about half of the system, which will comprise of 3 different single phases. So that is the first advantage. Second one, the operating cost. As we see, the current requirement here will be reduced. Why? The line voltage will be √3 times. So the current requirement, if this power is same, VI, let us say I am assuming unity power factor. If the power is same and I increase this, the current will be reduced. So the line to line voltage is increased. It is √3 times the phase voltage. So then the line current will reduce. So the amplitude of the current will reduce. It will lead to lesser I²R losses, and the voltage drop along this line will also be reduced. So I will have 2 more advantages. First one, the operating cost, the losses, the I²R losses which are going to happen in the lines are going to get reduced. Second one, I will have better voltage regulation. That is, there will be a very small change in the source voltage and the load voltage because of lesser voltage drop along the line. So we see that a 3-phase system is having lesser cost in terms of capital cost as well as operating cost. The next advantage will be time independent power, 3-phase power. How? We will prove this in the next slide. For proving this advantage that the 3-phase power is time invariant as compared to the single-phase power, I will assume that the system is balanced. The loads are balanced and the sources are also balanced. Let us say the voltage in phase A is VAN cos omega t. Then VBN will be VBN cos omega t minus 120 degree, and VCN will be VCN cos omega t minus 240 degree. And let us say the impedance is Z angle theta in each phase. So the current in the line will be IA is equal to IA cos omega t minus theta. That is, there will be some phase difference between the voltage and the current, which will be the impedance angle. IB will be IB cos omega t minus 120 degree minus theta, and IC will be IC cos omega t minus 240 degree minus theta. Let us see what is the one phase power first. The power in phase A will be VAN, and let us say we find the instantaneous power VAN into IA. It will be VAN cos omega t into IA cos omega t minus theta. Let's solve this. It will give VAN IA cos omega t into cos omega t minus theta. I will divide it by 2 and multiply it by 2. What it will give? It will give VAN IA by 2. Let us say it is root 2. These will become RMS values. And what it will be? Cos A plus B plus cos A minus B. So we see that the power in single phase will be time dependent. It will be pulsating. It will be changing at twice the frequency of the source. That is, if the frequency of source is omega and like that, then the power will pulsate at twice the frequency, at 2 omega. That is, the power will be time dependent. It will not be a constant. Now let us see the three-phase power. I already derived the power in phase 1. Let us find out what will be in phase B. It will be VBN into IB. On solving, we will see it will come out. Since I have taken this as balanced, I can write it directly VAN and VAN. The magnitudes will be same. It will come out VAN IA root 2 cos 2 omega t minus theta minus 120 degree plus cos theta. Let us say it is equation 2 and the first one is equation 1. Similarly, on multiplying, we will find the power in phase 3 will be VCN into IC. It will come out to be VAN IA root 2 into root 2 cos of 2 omega t minus theta minus 240 degree plus cos theta. Let us say it is equation number 3. The total three-phase power will be P3 phase. Let us say it is a function of time t, will be PAT plus PBT plus PCT. On solving, on summing from equation 1, 2 and 3, I will see it is going out to be VAN by root 2, IA by root 2, and this part which is time dependent, you see it is making a balanced three phase. The sum of these three, 1, 2 and 3 will come out to be 0. And the remaining part will be only cos theta in this, cos theta in this and cos theta in this. It will be 3 cos theta. That is VRMS, IRMS per phase into cos theta is the three-phase power. We see that the power is independent of time. It is a constant. and it depends only on the power factor or the impedance angle. So in the next slide we will see what will be the torque input. So the power delivered by, let us say, 3-phase motor is P 3-phase. It is instantaneous power 3 of V phase, I phase or I line cos theta over root 3 VL IL cos theta. Then the mechanic, let us say the efficiency is 100% or there are no losses in the system, then it is also going to be equal to the mechanical output or the electrical output, whatever we are considering. If it is a motor, it will be equal to mechanical output also and electrical input also. So the torque will be power upon omega, and omega is a constant. P is also a constant. So the torque on the shaft will be a constant. There will be no mechanical vibration because of it. And since the mechanical vibrations are absent in 3-phase as compared to the single phase, where there are going to be some vibrations due to pulsating nature of the power, we will see the 3-phase machines are mechanically more stable and makes less noise. Why? Because of the pulsating torque, the single phase machines will make more noise as compared to 3-phase machines. That's why for higher ratings, we usually use 3-phase machines instead of single phase machines. First, the input current will be less. Second, the power will not be pulsating. Third, it will be noiseless as compared to the single phase. These are the various advantages because of which we use 3-phase system in place of 3 different single phase systems.